Good morning. I'm Dr. Ben Hanson from University College London. I'm going to be presenting some slides on rheology and dysphagia, and then following the presentation, I'll be available to answer questions.
I'm going to start off by defining what is rheology. Rheology describes the relationships between pressure and flow of fluids and semi-solids. It's more than just viscosity, but we will define what that term is. We'll also see that there are other characteristics which describe the relationships, particularly involved with swallowing, and particularly for dysphagia management. We'll look at the role of rheology in dysphagia management, and that plays a part through the initial diagnosis of dysphagias. We'll look at therapy and how texture modification can be best used. We'll look at how understanding rheology can enable clinical research and the development of new and better products, and using standardized terms for creating uniform standards of care. I'll also describe my work on the International Dysphagia Diet Standardization Initiative, IDSI. We'll look at the origins and development of that, some of the initial evidence and the process of creating those international standards, all based on physiological rationale for different types of textures and particle sizes. And we'll look at some of the recent progress of IDSI around the world and how it's progressing. So I'll start right at the very beginning then, looking at a newborn, and we can see that eating and drinking are going to be fundamental to sustaining life and also our quality of life. From birth, the first interface that we have with the outside world is mechanical. It's a key interface between the human body and the outside environment, and we learn that suction creates flow of milk. The swallowing reflex is already very complicated, but allows us to process consumption of that milk, and to allow us to do that in all sorts of orientations as well, on our sides, on our backs. There's an enormous amount of information, sensory information, that comes from the mouth, and when we look at the brain and the somatosensory map, the mouth accounts for about 40% of the whole body. So that's more sensory information than comes from the hands. We can see then that it's very important to our perception of the outside world and our quality of life. Here we see a swallow in video fluoroscopic study. In this case, there's some aspiration, which is movement of the fluid bolus actually down through the larynx into the lungs. So that's representation of a type of dysphagia. What we're interested in is what's being controlled here. The liquid that you see in black there has no active behavior, it has no sense, it is just responding to the forces that are acting on it. And it's the role of the tongue and sensory surfaces inside the mouth and moving through the pharynx that control the movement of that bolus. When that system goes wrong, that's the definition of dysphagia, of oropharyngeal dysphagia. So there are various ways that we can approach managing oropharyngeal dysphagia, texture modification being one of those. Now it's quite widely used, whether it's explicitly called texture modification or not, but it's very poorly understood in general, and that's because in part we don't have the tools necessary to describe it or to understand it in the practical environment where it's used. So we have terms like coating the back of a spoon or slowing down the flow, but these don't necessarily represent actual physiological dysphagia. So looking at the swallow from a rheological perspective, and that's where my engineering background would look at it, we can see motion of the bolus gives rise to perception of that force and motion by the body, and that controls the actual response that our body provides in terms of moving and applying pressure to the bolus, and then of course the bolus moves in response. So we have a cycle of the control and sensing aspects of a bolus to ensure that it's swallowed safely. And right in the middle is where rheology sits. So that is the science that relates pressure and flow. If we look at the flows that occur during swallowing, remember we're focusing on the fact that flow is occurring as a result of pressure and forces acting on the bolus. So here I've tried to represent that using arrows, black arrows representing gravitational force and red arrows representing force provided by the body. The tongue controls and moves the liquid to form into one bolus in a cup, and then a muscular propulsive wave pushes that bolus posteriorly. And we have a peristaltic flow down past the pharynx, past the larynx, through the esophagus. So now if we think back to what are the pressures and flows acting on the bolus, we can think in some more detail about what we are trying to achieve with texture modification. And there are various aspects to that. We want to make hard foods flow more easily, and so in some cases we will liquidize or puree foods, and we in some cases want to make fluid liquids move less easily, so we want to thicken those up in order to provide more time to prepare for a swallow. So all of this control is about adjusting the relationship between pressure and flow. Now that relationship between rheology and dysphagia needs more scientific research, and in order to do that you need to be able to quantify the consistency. So we're going to look at ways that you can actually measure rheology and define certain types of liquids and solids using standards that are worldwide. And assuming that's possible, these rheology concepts can be used to design texture modification approaches and strategies and products in the future. And with those standardized products, we can aim for standardized care, not just in different institutions within one country, but different institutions around the whole world, and standardizing within one institution to go from diagnosis through to care in the hospital setting and also in the home setting. Now when we're looking at rheology, there are different types of flow and deformation that can occur. When we're drinking, one of the main types of deformation is called shear flow, and that's when you have layers of a liquid sliding and moving across each other like this, and that's easy to visualize in a straw. Then when you look at the flow resulting as a response to pressure applied, the rate of flow depends on the magnitude of the pressure that you're applying. So you apply a low pressure and you get a slow flow. Apply a higher pressure and it's the rate of flow that changes. Not the total amount of liquid that moves, but it's the rate at which the liquid is flowing. So on a graph, we can plot that to get a characteristic for a certain type of liquid. The simplest characteristics of liquids are called Newtonian fluids. And if you look at the graph here, we've got on the y-axis shear stress, and that's thought of as how hard you need to push the liquid. On the x-axis, how fast the fluid is flowing as a result of that pressure. For Newtonian fluids, you have a straight line relationship between the two. Push harder and the fluid flows faster. However, most of the liquids and semi-solid foods that we would consume don't have a straight line relationship. They have a slightly curved relationship, usually with this sort of shape, so that the viscosity is not a straight line, but it's a function of how hard you're pushing. When you're only applying a very low pressure, and that could be, for example, when you've just taken a spoonful of some pudding, the material apparently has a very high viscosity. It doesn't move very fast in response to that. In fact, for some puddings, they might even appear to be solid, i.e. there's no flow whatsoever. But once you start applying a pressure to them, and you move up the graph, then the fluid flows much faster, proportionally more than you would expect. That gives the liquid a lower apparent viscosity. So it's quite complicated to characterize the viscosity for a particular material, And that's why for most foods and drinks, you can't say that they have a certain viscosity of any particular value. It depends on the rate at which they're assessed. Here, for example, we've tested at 4 points, shown as the 4 dots on that graph, and that would correspond to 4 different apparent viscosities. And for a particular liquid, that tends to be plotted on a graph of apparent viscosity versus shear rate. That's gamma dot on the x-axis. So you can see it's not a constant value for a particular liquid. It varies depending on how fast you're testing it. Maybe that's easier to visualize looking at the actual test equipment. This is a rheometer, and you take a small sample of the fluid, 1 milliliter here, and hold that between 2 surfaces, one with the shape of a cone and one with the shape of a plate. Now as the cone rotates, that creates a steady rate of shear. Remember that sliding of layers of the fluid. Steady rate of shear throughout the fluid. The machine measures the amount of torque, that's a turning force, measures the amount of torque required to induce a certain speed of rotation. And from that, it infers the shear stress and shear rate within the fluid. Plotting that on a graph, this is some real data, and you can see in this slide honey, quite a liquid honey, and this has been tested over a range of shear rates, and you can see that that's quite a straight line graph, so that's quite a Newtonian fluid. But when I add a smoothie, a strawberry and banana blended drink, you can see that has the curved shape that I showed you before, and that means that its apparent viscosity is not one constant value but varies. For the honey, if you look at the right hand graph, the honey has a relatively constant apparent viscosity, in this case of 10 Pascal seconds. But for the smoothie, the apparent viscosity changes depending on how fast you're testing it. So the big question is, which liquid is thicker? And it's very difficult to assess that. If you look at low applied stresses or low shear rates, that's to the left-hand side of the graph, the smoothie has a very high apparent viscosity, higher than honey. So, for example, the smoothie might be able to stay on a spoon better than the honey. However, if you try to drink those liquids, then you'd need to make them move much faster, and in that case, the honey would have a higher apparent viscosity than a smoothie. And that's what you could imagine in a thought experiment. If you tried to imagine drinking a glass full of honey, that would be very difficult. So I think you can see it's quite difficult to match rheological profiles of liquids to how they would be perceived in the mouth. Now, many conventional food and drink products have somewhat similar shear thinning properties. That's the fact that the apparent viscosity tends to decrease the faster you move them. Or another way to think about that is that as you apply more and more pressure to the fluids, they respond by flowing with ever increasing velocities. Now, this is probably a good thing in terms of evolutionary approaches to eating. It means that they're actually quite easy to control in the mouth. This is the oral phase. The liquid in this case won't flow at a very high speed unless you actually apply a pressure to it. So it, in theory, would only respond to movements when you push it. In the pharyngeal phase, then, having a shear thinning property is also beneficial in that respect, that you want the material to be able to flow quite quickly, but you don't want the person to have to apply a very high pressure to it. That would result in fatigue and it would feel effortful. So for a shear thinning liquid, you get faster motion without requiring excessive pressure. Now this is just a theory, and we're mapping this to measurements that have been taken on the rheometer in the lab. What actually goes on in the mouth is quite hard to visualize. Here we've got some data from a paper in Applied Rheology about trying to measure the bolus using ultrasound. It's very difficult, it's very grainy, there's very little contrast between a bolus and the tongue. It's very difficult to measure in MRI or X-ray. There are some interesting studies now using CT movies that capture images at 10 times per second. But it's generally quite a challenge to image that. And it's also very difficult to simulate it with a computer. Computers need very simplified models of fluids, and to model the interaction between that fluid and our anatomy and how that changes in response to the presence of the fluid is very difficult. Let me show you what we're doing at UCL to simulate it, and this is a quite simple simulation of some of the aspects of oral processing. We have a simulator, a mechanical simulator, that's aiming to duplicate an aspect of the tongue as that compresses a bolus against the hard palate. Here you can see what happens in ultra slow motion. This is 1/20th of the speed. We've put a fluid bolus in there and it's being compressed. And while it's doing that, we're measuring the pressure at 5 points across the palate. We're also able to capture the flow of that liquid using a system called particle image velocimetry. And you can see that the little particles in the liquid, just micro bubbles, light up, and we're able to use computer image analysis to map the flow through the bolus. So while we're not able to see in vivo what the pressure and flow are, we can see in this in vitro simulator how any particular liquid or texture modified product will behave. So this is enabling us to calculate what the pressure and flow relationships are. So you'll remember I was describing the fact that the apparent viscosity of a liquid varies depending on how fast you're moving it. So the central question is, how fast are liquids being sheared when they're in the mouth? And this system allows us to measure that for a variety of different swallows, whether that's healthy or dysphagic, whether the tongue is fatigued or maybe has a different amount of saliva coating. In this particular example, we can measure that the shear rates vary between 0 and about 25 reciprocal seconds. So we can then look back to our graph of the fluid's rheology, and here we have apparent viscosity plotted as a result of shear rate, and we can then work out whether a particular liquid would be harder or easier to swallow. So this is aiming to allow the design of better and more easily swallowed fluids. This slide is actually describing a study that we've done where we've matched two fluids. One is starch-based and one is gum-based. We've matched those to have exactly equal viscosity at one particular shear rate, and the rate we've chosen here is 50 reciprocal seconds, as that was used as the basis of the previous National Dysphagia Diet Standards from the United States of America. And it's worth mentioning that those standards are now being superseded. They're being taken over by the International Dysphagia Diet Standardization Initiative, the IDSI standards. But we wanted to work out how reliable was this 50 reciprocal seconds measure. So we put those liquids in the simulator and found that gum behaved differently to starch, as you may expect. Now, if you look at the viscosity graph on the top left, you'll see that those two liquids have different slopes. The gum-based liquid has a steeper slope. That means it's more shear thinning. So the difference in its performance at low levels of stress is exaggerated compared to starch. And what we find is that in order to clear the bolus, in order to remove it from the oral cavity, starch needed a much higher pressure than gum, even though they both had exactly the same viscosity at 50 reciprocal seconds. So this is really illustrating in a quantified test how In the one hand, measuring at 50 reciprocal seconds, measuring viscosity is not adequate to describe the liquids. And also the fact that gum-thickened liquids may be easier to swallow if for a given level of thickness. Starch has been reported to leave higher residue for a certain thickness. And this simulation, this experiment, reveals one mechanism why that might be the case. Now, there are further influences of rheology that might play a part in practice. We've mentioned shear thinning viscosity, but even with that, that doesn't describe all the characteristics of materials. Viscoelastic materials, such as this jelly shown here, that can spring back. It can have an elastic component, sometimes even bounce. And cohesiveness is a very important aspect too. Some types of jelly will fracture into large pieces, but other types of jelly may dissolve more into a sort of paste. So in that case, that's not to do with rheology, or not to do with viscosity, it's to do with cohesiveness and the fracture behavior of materials. And the final component, which is very important, is tribology, which is the study of surface interactions, often to do with the lubrication of oils in machinery, but it's very relevant in swallowing too. In particular, if you think of swallowing an oyster, shown here, the bolus itself can remain whole, but you're able to swallow it because there's a slippery surface coating. And in practice, saliva or some of the texture modifying gels can make some boluses very slippery. So the flow that goes on within the bolus is very different. And again, this is something to consider. This may be more or less suitable for different types of patients and different types of dysphagia. The point is there are all sorts of ways that you can apply texture modification to give you a safer and more easy swallow, as long as you know a little bit about some of the properties of materials. The final property to cover is called yield stress, and this is the amount of stress that a material can withstand before it flows. So some materials, if you take a little molded cylinder of a semi-solid liquid here, it will slump down and then it will remain in that position indefinitely. So it's still quite soft and quite fluid, you'd be able to swallow it very easily, but it's not moving at all, it would appear as a solid. And that appearance is due to its yield stress, which is a separate aspect from viscosity. How that manifests in practice, yield stress is usually a very weak force, so it doesn't really affect the amount of pressure that your tongue would need to generate to swallow liquids, but it is significant for residue, so it would affect the amount of residue or the coating seen on walls of a glass or beaker or on the back of a spoon. And that's interesting because the guidelines from the UK used to rely on assessing a liquid based on whether it coated a spoon. And actually this was much more of a measure of yield stress rather than a measure of viscosity. So we're moving now into thinking about how to classify liquids based on their rheological properties. And we've seen that viscosity is not adequate to completely describe liquids. And we've seen that measures such as coating or a yield stress test may also only measure a part of the story. So let's look at a summary of different types of material, different types of measurements that you could use to assess what we would call thickness. From the top, we have the most subjective and least scientific, perhaps, measures, which include just describing the liquid with words. And this is very challenging because everybody's interpretation of words are different, and it's dependent on your own personal experience of certain types of liquids. And then we move down to physical assessments, visual assessments, and sometimes these can have quite a good correlation to the actual thickness. The difficulty comes where you're trying to assess between different types of liquids, for example a starch versus a gum, or a clear liquid versus a liquid that's coloured or opaque. Moving down, then we have consistometers and line spread tests and syringe tests. These give a numeric output. They don't assess the liquids in a very unified or uniform manner, but they can be quite repeatable. More involved than that is a viscometer. Now, this is not necessarily more scientific or more accurate. The very bottom test that I'm suggesting there is a rheometer, which does give you a very thorough and complete study in very controlled conditions. This is where you take one small sample of the material and compress it between two plates. Is that very realistic of a swallow, though? That is the question. It's very controlled conditions, but not necessarily representative of a whole bolus. So even with a very expensive rheometer, the accuracy or the transferability of that to dysphagia is sometimes questionable. It's with this context of standardizing in mind that I'm going to talk about the International Dysphagia Diet Standardization Initiative. Now, I sit on the board of this group, and it's a very interdisciplinary group. We have speech and language therapists, dietitians, occupational therapists, nurses, and food service professionals. So it covers a very, very wide range of abilities, and it also covers situations from all across the globe. So we really do have representation from all the populated continents, as well as all sorts of different developmental stages. The main focus is safety. We're aiming for common terminology and a quantified framework to assess thickened liquids and texture-modified foods. The background to this is that in 2013, we started to look at what are the existing guidelines in place with all different situations around the world. We then started to look at what evidence there was for texture-modifying foods. And we did a systematic review that was published in the journal Dysphagia. This is available open access. And the results of that were that thickened liquids can help those who aspirate thin liquids, i.e. if you're aspirating water, then thickening the liquid, there was some evidence that that would reduce penetration and aspiration. But there was also evidence that liquids could be too thick, where residue became to be an issue. That also creates risks in itself and also tends to reduce the compliance of a person with that diet, so maybe their fluid intake would reduce. When we looked at the evidence regarding texture-modified foods, there was very much less data to find. And partly one of the reasons for that is that it's very difficult to actually conduct a randomized controlled trial on the safety of thickened foods if your outcome could be that one of your subjects would choke. So actually getting ethical approval for a study where death is part of the study is very difficult to do. So that's some explanation of why that's hard to find, but we did find data through autopsy studies where people would analyze what's left in the airways and tracheas after somebody has actually died from choking. From this, we can determine the range of safe or unsafe particle sizes, and it's that that's formed the basis of our guidelines for texture-modifying foods. For example, in an adult population, the size of the typical tracheal opening is around 15 to 27 millimeters for males and 13 to 25 millimeters for females. So as long as a particle of food is smaller than that, that should enable it to pass through the airway instead of becoming lodged and occluding the airway. We also wanted the guidelines to be based on anthropological data. So we looked at the physiology of developing swallowing and how your oral processing capabilities increase as you develop. Taking all this together, we then followed guidelines for creating these international guidelines. We followed the best practice recommended by the World Health Organization, Council of Europe, and the UK's National Institute for Health and Care Excellence. And that process was as follows. In 2013, we created a multidisciplinary group of individuals. We then involved the consumers and did surveys and stakeholder groups. We identified the clinical issues that were involved. We carried out a systematic academic literature review, and that I've described, and did extensive consultation in situations all across the world. We then drafted the framework that we're calling the IDSI Texture Modification Framework, and that's subject to a final review via survey, and we had over 3,000 respondents from 57 different countries, as you can see, distributed all over the world. So here is the finished framework. We've classified foods and drinks on a single continuum with 7 levels of thickness plus unthickened liquids. In the middle, foods and drinks overlap, and those share the same texture attributes. We wanted to make that distinction so that it doesn't matter whether you classify, for example, a soup as a food or a drink. That level of classification is very difficult and very subjective, and we wanted this framework to be based purely on objective and clearly defined measurements. I'll look at each level in a little bit more detail now. All of these descriptors are available on the website, idsi.org, and you can see each description starts with the physiological rationale for this type of thickness. We looked at classifying physiology first and then matching a texture to that. Here's some further details, and we're looking at the process of breaking down food during chewing. So starting with our level 6, which we're calling soft and bite size, we're defining soft by applying a constant pressure to it and assessing the level of breakdown of the food. We're using a fork and applying pressure with the thumb until the thumbnail starts to blanch white. Now that pressure is being exerted so that the blood from your capillaries is squeezed out, and when your thumbnail starts to blanch white, the pressure is exceeding the systolic blood pressure, and that's corresponding to roughly 17 kilopascals. We've tested that in pressure sensing devices, and 17 kilopascals is comparable to the pressures that are exerted during swallowing. So we're defining bite-sized as 15 millimeters squared, and that's got relevance to the tracheal size, as I described before, which we've identified from autopsy studies. Moving on to level 5, our minced and moist level, we're defining 2 to 4 millimeters as being an important size of particles there. Now that's got relevance to the particle size of a chewed bolus, and this has been identified from studies where individuals have been asked to chew an item of food and then expectorate it, spit it out, when they felt it was ready to be swallowed. So our level 5 corresponds to a type of material that would be tolerable to be able to be swallowed without a great deal of biting or chewing. So that maps back onto the physiology then of certain patient groups. Moving on to level 4, our smooth and moist bolus, we need this to be smooth and lump-free and moist so that it's able to be swallowed with very minimal oral processing at all. And again, that's mapping onto physiology and patient groups where any degree of oral processing is going to be too much. When we move on to classify liquids, we've developed a flow test based on a universally available 10 milliliter syringe. Now this is based on a larger syringe that used to be used in the dairy industry in the Netherlands, and I believe in Brazil a similar posthumous funnel is used to classify liquids that are used for dysphagia. Our syringe is 10 milliliters, so it's quite a small volume of liquid, and it is able to classify liquids from water right up to the very thickest liquid that will actually flow, and we've got that as a fairly uniform spread across the categories. I'll show you an example of how that works. Here you can see 10 millilitres of the fluid in the syringe. You need a stopwatch to time it, and you let the liquid flow for 10 seconds, and then at 10 seconds you put your finger over the end, forming a seal, and the amount of liquid that's left in the syringe at that point determines how thick it is. We can map that to the IDSI levels, and in this case there is 2 millilitres of liquid left, and that falls into IDSI level 1, the grey level there. So you can see for thicker liquids, they will flow less from the syringe and leave a higher number in the syringe. So we have a nice sensible mapping of higher number gives you increased thickness. Level 4, there will be no flow through the syringe, and we would recommend that you use a fork and a spoon to test that liquid instead. Some details of the measurement techniques. We've published, and I should draw your attention to these, all these publications are open access, mostly in Dysphagia, the journal. In fact, our publication of the IDSI framework is actually their most downloaded article in their history. We've also published a pilot study that was done in Kempen in Germany, and that describes the whole process of implementing it in practice. We've received numerous letters of support, and adoption is in place in various situations around the world. Australia, New Zealand. New Zealand will probably be one of the first to completely adopt the system in January 2018. The North American Academy of Nutrition and Dietetics is recommending the adoption of International Dysphagia Diet Standardization as from next year, and that's replacing the National Dysphagia Diet. We've also got uptake in China and Canada, again where the IDSI framework is being adopted across the board. The methods are being incorporated into university courses. And I'd just like to draw your attention to the resources that exist on our website. You're allowed to reproduce and use those for training. We have a Creative Commons license to allow you to do that, and translations are underway in at least 14 different languages. We also have apps for iOS and Android systems, iPads and tablets. And our website is the main resource for staying in touch, www.iddsi.org. Most of the material that I've presented today is available on there, and there are email addresses to communicate more information if you need it. So that concludes my presentation, and if our video conferencing facilities work, I'll be more than happy to take some questions in person.